Hello again, everyone. We are going to continue working with quadratic functions. In our last video, we showed how to graph quadratic functions if they were given to us in something called the vertex form. And that was really nice because we can get the graph of a function very easily if it's given to us in vertex form. We think about the basic graph of y equals x squared, and we look at the vertex form and see what shifts, what transformations need to be done to the graph. Sometimes quadratic functions are given to us in what's called general form, and that's this right here, ax squared plus bx plus c. Okay, so when I have a quadratic function in general form, I like to make use of this vertex formula to do a lot of the work. Okay, so suppose somebody gave me this problem and they challenged me to rewrite this in vertex form. Now, one thing you could do is a technique called completing the square, but I like to actually use the vertex formula and work backwards from that. Okay, so let me apply the vertex formula to this problem. A is 2, B is 4, C is -3. Okay, so the vertex formula says that the x-coordinate of the vertex, because we know we've got a quadratic, the graph is going to be a U-shape, the fancy name is a parabola, and the turning point of that U-shape is called the vertex. If we know where the vertex is for our quadratic function, we're more than halfway home. Okay, so the x-coordinate of my vertex is going to be -b over 2a. So -4 over 2 times 2, so -1. The x-coordinate of my vertex is -1. Now, to get the y-coordinate, I take this value and substitute it into the function. Now, of course, we remember from the very beginning of the course how function notation works, right? If you put -1 there, you replace this x with -1. So it's -1 squared. And you replace this with -1. All right, so 2 times -1 squared plus 4 times -1 minus 3. Okay, very important here, -1 squared means -1 times itself. You square -1, you get +1. Times the 2, we got a 2 right here. -4, 2 minus 4 is -2, minus 3 is -5. Okay, so the vertex of my quadratic function is -1, comma, -5. So if I know that, I can get back to my vertex form. Okay, now, notice that when we use the vertex form, that was like this. You remember that from the last video? Okay, notice we use the same letter there. Okay, if you have a multiplier there, you're going to need that same multiplier. Okay, we're using the same letter in the same context of quadratic functions. It's got to stand for the same value. So if my a is 2, then my multiplier out front is going to be 2. All right, now, if we remember this scheme, subtracting would move my graph to the right, but I've moved to the left because my vertex is at -1. So this would be x plus 1 squared and then -5. And so that is the equivalent function in vertex form. If you don't believe me, take this and square it. You would get x squared plus 2x plus 1. Multiply in the 2. 2x squared plus 4x plus 2. Subtract the 5, and you get a -3 on the end. Okay, so if you expand this out, you do indeed get back to our original function. All right, next thing I'm challenged to do is sketch the graph. Okay, so I need a little space. Now, once I've got it in vertex form, this is a breeze. You remember from last time. So I'll draw myself a little grid. I'll be careful to make my tick marks evenly spaced. Okay, so the lead coefficient is positive, graph opens up. Shift 1 unit to the left, 5 units down. Okay, my vertex is right there. Okay. Now, I'm thinking about my basic graph y equals x squared. If you look back in our last video, I kind of made a big deal about the jumps. Like ordinarily we would go over 1, up 1. Well, this has a multiplier of 2. That's going to give us a vertical stretch. We're not going to go over 1, up 1. We're going to go over 1, up 2. Okay, over 1, up 1, 2. Over 1, ordinarily we would go up 3, but that multiplier means we're going to go up double that. 1, 2, 3, 4, 5, 6. There's another point on my graph. Okay. Once again, connect these with your nice smooth curve. Don't forget your axis of symmetry. Very helpful for getting additional points on the graph. Okay, so at this level, at that point, that means I've also got that point. I'm seeing here, I've also got here. Once again, nice smooth curve, joining these points. So this is my graph. Okay, either formula works, it'll give us the same graph. Okay, so what is this saying? This is saying that 0, -3 should be on the graph. It's really easy to see from here. You plug in 0, that goes away, all you're left with is -3. Okay? This is what, -1, -5. Saying if we plug in -1, we should get -5 out. Okay? Then we've got this over here. Okay, so sketch the graph. If you're given something in general form, I use the vertex formula to find the vertex. Now, you don't necessarily need to write down the vertex form because you've already got all the information you need. You know where the vertex is, and you've got your lead coefficient from the general form, so I didn't necessarily need to write this down. It's just fun. Okay, so we got the graph. Okay, what's the minimum or maximum y value? Well, in this case, we're going to have a minimum y value. Our graph is a U shape, a parabola opening up. The vertex is going to be the lowest point on this graph. Okay, so many of these quadratic functions, problems involving quadratic functions boil down to finding what the vertex is. If you can do that, you've got everything. Okay, we can answer a couple of other questions. What's the axis of symmetry? The axis of symmetry is x equals -1. We could say, where is the function increasing and where is it decreasing? The function is increasing on the interval -1 to infinity. Remember how to read that from a graph? That's where the graph is sloping up. Where is the graph sloping up? Well, it's sloping up to the right of this vertical line. What is this vertical line? It's x equals -1. So the graph is increasing on the interval -1 to infinity. Where is the graph decreasing? Well, the graph is decreasing on the interval -infinity to -1. What's the domain? The domain for any quadratic function is always -infinity to infinity. What's the range? The range, you remember, the range of a function is the set of all possible output values. The points on the graph of a function are input-output pairs. So finding the range boils down to finding what are the possibilities for the y coordinates on the graph. Well, -5 is the lowest y value. So the min y value is, we decided the min y value here was -5. That means the range is -5 to infinity. Okay, so many questions we can answer without doing tons of computations. We just need to look for the key information. And that's going to be a theme going through this course. For every class of functions that we deal with, for every different type of function, we're going to have different key information. When we were dealing with linear functions, the key information you need to know is what's the slope, what's the y-intercept. If you know that, you can basically answer any question I can throw at you about those linear functions. For a quadratic function, the key thing is, what's that vertex? You find the vertex, you can tell me a lot of stuff. You need to know the lead coefficient too. So for linear functions, you're looking, what's my slope, what's my y-intercept? For quadratic functions, you're saying, what's my vertex, what's my lead coefficient? If I've got that, I can put things together and answer just about any question about a quadratic function. Okay, so look for the key information of the vertex and the lead coefficient. If the function is given to you in vertex form, then there's really no work to do. You can just pull the vertex right off. If the function is given in general form, then this vertex formula comes in really handy for getting the information we need.